In this video, we're going to show you some basic information about setting up a scientific graph. Now, while this is not complicated, it is a little bit different than the way you do things for a typical math graph, so we want to emphasize some of the differences here. So when you are making a graph in science, of course, the whole point is to try to determine a relationship between variables that you are testing. And a graph is just a visual way that we can help to try to see and to try to determine those relationships. So when you are making a scientific graph, the very first question you want to ask yourself is about the variables. Okay, you want to identify who the independent variable in the experiment is. Now, sometimes that's called the manipulated variable. And keep in mind that the independent variable is the thing that the scientist is changing. In other words, it's the thing that the scientist has direct control over in the experiment. And when you're making a graph, it's important to identify who the independent variable is first, because that is the one that gets plotted along the x-axis. Okay, then you also need to identify who your dependent variable is, or sometimes that's called the responding variable. That's the other thing that you are measuring to see, well, how is this affected, how is it responding as I change my independent variable? And that gets plotted on the y-axis. So for example, let's say we were doing an experiment and we wanted to see if adding Miracle-Gro helps tomato plants grow taller. So maybe that's my experiment. I'm going to give some Miracle-Gro to some plants and just water to other plants and more Miracle-Gro to some other plants, and I want to see how tall they get. So take a minute, pause the video now, and write down who would be your independent and who would be your dependent in that experiment, and then click play to check to see if you're correct. Alright, well, if you said that the amount of Miracle-Gro that we added was the independent variable, you would be correct. Again, that is the variable that the scientist is in direct control. We would be giving none to soap plants, a little bit to some more. I'm directly controlling that. The responding, the dependent variable here is, well, how tall are the plants going to grow in response to the amount that we give them. So we would identify who that is to help us set up our graph. Let's practice another one here. Here's another example. You can read through this scenario and identify who the dependent independent is. Again, pause this and then click when you're ready. All right, checking our answers. If you said that the mass of sugar was the independent variable and the density of the water was the dependent, you are correct. Again, notice our labels. We have good labels here. We're not just saying sugar. We're not just saying mass. We have a specific label where we're saying mass of sugar, and not amount. Stay away from the word amount. That's a very vague word. It's not specific. If I measure the amount of sugar, am I measuring the mass of it? Am I measuring the volume of it? Am I measuring how heavy it is? Am I measuring how many cubes of sugar I'm using? Okay, all of those would be an amount. That's a vague word. So be specific. Mass, volume, density. Okay, good. If you got that right, excellent. Now, another thing you need to think about when you're setting up a graph is you want to make sure you're labeling things very carefully. So again, as we just mentioned, when you label your variables, you want to make sure you're being as specific as possible, and if possible, using your two words. You need to always at least have the type of measurement that you're measuring, like mass, volume, density, temperature, length, and so forth. And when you set up your axis labels, the units go in parentheses behind the label, and you'll see our examples coming up in a minute on that. Also, you need to make sure that your graph has a good title. Now, a bare minimum, what I call the safe auto approach to making a title, is just simply listing your two variables, your y versus x variable. For example, if I just said mass versus volume. All right, that's the safe auto title there. I've got the bare minimum I need. Both variables are listed. But that's not a great title. I can read that. It doesn't give me a very good idea what the experiment is about. Okay, you can very easily, and without taking a lot more time, give a much better title that gives me a good idea what the experiment is about. And a generic formula that seems to work a lot of the times, especially in our chemistry graphs, is by using this format, this kind of a template here, where you say the effect of, pop in your insert independent variable there, on, pop in your dependent variable there, of whatever you're testing. So for example, In our we could say the effect of percent sugar on density of water. That would be a good title for that experiment that we just read about Joe doing. It's not horribly long, but when I read that title, I can pretty much tell you a lot about what the experiment was that he did, as opposed to just saying percentage versus density or something like that. So another example for our Miracle-Gro graph, we could say the effect of mass of Miracle-Gro on the height of tomato plants. Again, that's not a ridiculously long title, but it gives me a lot of information about what the experiment is about. Just a little grammar note, be careful with effect. There's two words that kind of sound the same. There's effect with an E. When you're using it as a noun, you want to use the E in front of it. The effect spelled with an A, that is the verb. For example, if I said, the amount of sleep I get affects my performance in school, well, here I am using it as a verb, so I'm using the A version of this. Or if I said one effect of getting no sleep is that I get tired in school, in this case we're using it as a noun, so we would use the E form of it. So just be careful with that. We tend to use these words a lot in science, and they get mixed up a lot. So a little grammar note on the side. Back to our graphing. Let's say we were making a graph of Joe's experiment here. We've got the effect of sugar. Notice we put a good title in there. We've got both variables listed. We've got the percent sugar as our independent variable and the density as our dependent variable. And notice we've plotted them on the correct axis. Since the percentage of sugar is what Joe was directly controlling, how much sugar was he putting in the water, that's the independent variable, that goes on the x-axis. The dependent, the density of the water, that goes on the y-axis. So notice how we set that up properly. Notice we have units for those labels. We have grams per milliliter afterwards. Now just a note, I could also have said density of water. That would maybe be a slightly better label for this, but we at least have to have the word density there. And notice for my x-axis, the unit is actually just a percentage. And so we just put the percent sign in there. So there's a good setup for our graph. Now here's an example that's not so great. So pause the video. There are at least six errors here. So pause the video, see if you can identify them, write them down on your paper, and when you're ready, click to play to see if you've identified them all. All right, hopefully you were able to find 6 things, and let's see if you found them all correctly. First one is more of a grammar issue here when you are making a title. Just like a title of a magazine article or something, every major word should be capitalized. So we capitalized tomato and plant, so we should have been consistent and capitalized those other words as well. Another thing we should have noticed is that we've got the variables switched around. Okay, the Miracle-Gro, that was what we were controlling. That's the independent variable, so that should go down on the x-axis. And then the information, how the tomato plants respond, that should go on the y-axis. So we had those mixed up. Another thing is they use the wrong form of effect. Here they are using it as a verb, so we should have used the A version of that. Fourth thing, title's not a very good title. They've only got one variable. Okay, how the height of tomato plant is affected. Well, what's it affected by? They didn't mention anything about Miracle-Gro in our title here. And that, of course, is an important variable. That should have been in the title. Another thing is the units. The labels here are very poor. Tomato plants. They don't tell us what about the tomato plants they're measuring. They should have said height of tomato plants in this case. So very poor label on that case. In the other one, the word amount. Again, we want to stay away from the word amount. They should have told us what were they measuring about the Miracle-Gro. The mass, the volume, what was it? Should be more specific than that. And then finally, we've got no units. Both of these labels should have units after them. Maybe meters in parentheses if we're measuring the height. Maybe grams in parentheses after the Miracle-Gro if we're measuring the mass. So make sure we've got all those elements included. Okay, here's an example of a much better setup for that experiment. And you notice, again, we've got lots of our information. There's our units. Things are on the right variables. So always ask yourself those questions. Finally, the last and probably the most difficult thing when you're setting up a good scientific graph is the scale. And we are interested in a specific range of data, and we want to look carefully at the pattern. So we want a scale that is zoomed in so that our graph fills the paper. And this is the most troublesome thing when you're doing it by hand, because you want to make sure that your range that you have data for is actually what you're setting up on your labels. So you want to look at your range and see, well, what's the lowest value that I have information for, and make sure that goes near the one edge, and the highest value should go near the top. And a good guideline is you want to set it up so that your graph is covering at least 75% of the paper. And we'll show you what we mean by that. Scale does not have to start at 0, 0. That does not have to be the corner of your graph. If you have information near 0, then yeah, start at 0. But if not, start near your lowest data set, and we'll show you some examples of that. Also, when you're trying to figure out what scale to use, try to make every block equal to a nice number. Okay, 1s, 2s, 4s, and 5s, or any multiple of those like 10, 100, those all tend to divide pretty evenly, so they work very well. The ugly numbers, not that you can't use these, but it's very difficult to subdivide if you're saying that every block is equal to 3, 7, 9, 6, and so forth. So I recommend staying away from those. So let's look at another example here. Let's say here's a description of a experiment. So take a minute, identify your dependent, independent, pause it now. All right, hopefully you filled in temperature as the independent variable and volume as the dependent. So let's take a look at a graph of this. So if we're setting this up, again, what axis does the independent go on? Well, hopefully by now you know that's got to go on the x-axis, so there's our temperature. Dependent goes on the y, so we would put volume there. A good units that we put in there, they need to go in parentheses afterwards. And a good title here would be effects of temperature on volume of a balloon. So we'd have that set up. Now if you notice our graph here, these circles aren't easy to see, but you can see these are the data points. Okay, we tested this balloon at temperatures of 20, 25 degrees, 30, 35, and 40, and we measured what the volume was at those temperatures. So notice how that these points are spread out so that our graph is filling the window quite nicely. Now here's some examples of what you do not want to see. Notice how in this graph we plotted our points. The highest temperature we had the balloon at was 40, but yet we hit 40 right away. We have all the rest of this stuff where we have no data for. So there's a lot of empty space. The line's pretty much almost straight up and down. You do not want your graphs to look like that. Here's another one where, again, the biggest this balloon got was like less than 3 liters, but yet for some reason we have the scale going all the way up to 20 liters. So when we plot our points here, again, we have a lot of empty space. Our line is pretty much flat. You do not want your graphs to look like this. Here's another example of a poor scale. Look at all this empty space here. We're only using this amount of range that we actually have data for. A lot of empty space down here. We should not have started this graph at 0. Since our lowest volume was about 1 point, it looks like about 1.5 or something, then we should have started down there with 1.4 or 1.3, something in that area. Now the x-axis scale on this is just fine because there's our lowest point, there's our highest point. That is spread out to fill it just nicely. So let's have you practice one on your own. Here's some data. Take your graph paper that I've given you and set it up well and plot these points. Think about what scale you're going to use. Make sure it fills the window. And then again, click on the video again to play it, and we'll check to see how you did. All right, if you set up your graph well, it hopefully looks something like this, where you have your variables on the right place. You've got a good title. We should have Miracle-Gro, the mass, on the x-axis, and you should have your points plotted. Notice we should be filling the windows, so I went to 8 on this one, and it may or may not fit what you have on your paper, but this point here should be near the edge, and your low point here should be near the bottom of your paper. And we've gone from there. Now, once you have your points plotted, we want to analyze the data. Now, you don't want to play connect the dots, where you're just connecting one point to the other. You may have done that in some previous graphs, but what we're interested in is there a relationship? And in this case, this looks like a linear relationship. If I imagine it, now it's not a perfect line. In science, our data does not come out perfectly, but overall, this is pretty linear. If it were curved, we would see more of a swing, a consistent swing to this. But this definitely is pretty linear. So what you want to do is draw a line that comes the closest to hitting the middle of these points, such as that one there. Okay. When you make your line, You want to make sure you have about an even amount above and below. Okay, so take a minute now and go back to the graph that you just made of your Miracle-Gro, and you have your points already plotted on there, and go ahead and draw the best fit line. Pause the video now and click again just for our final comments here. Alright, check your graph with this one, and you can pause the video now and just analyze what we have here. Take a look at the way the points are, how this is kind of in the middle of the points. Notice when you look at these points, say this one here is pretty far above the line, but this one over here is about an equal distance below. So look on yours. Did you hit it pretty well so that your line was in the middle of those? You don't want one way up above and the other one like just a tad below. Again, the idea is it should be in the middle. So for everyone that's pretty far above, there should be one about an equivalent below. Here's two more equivalents here. And this one came pretty close. But notice this did not hit any of the points. I had the computer do this, and you can compare this with yours to see how it compares. Be sure to view part 2 of this video series to look at some tricks for analyzing that best fit line that we've just drawn.